I'll do one today. So I know some of you had asked me to maybe talk about networking, and I was like, okay, I can talk about networking. If anyone has any questions about networking, I'm glad to talk about networking. So think about questions you have on networking. So I've got some material prepared before we get there. Actually, I could do that. Questions about networking? Yeah.
Backbones.
What?
Backbones.
What about backbones?
How they work and like how they.
Like spinal cords are very important, man. Okay, how do they work? Well, so
What are they?
what are they? Yeah. Don't worry, I'm not going to dive into talking about exchanges. So there's a weird thing about the internet. I mean, did we talk about exchanges and things like that in class? No. Okay, so. When you hear about the internet, right, people tend to think that the picture of the internet is a bunch of nodes and it's a graph, right? It's the classic graph, right? And physicists get all excited because they think they know a lot about graphs, and then they come up with all sorts of crackpot theories about graphs. Okay, so there is the internet, right? And the whole point about the internet is it's meant to have some stability properties, and this will actually relate to what we talked about when we talked about MST, right? When we did Moravian, the whole Moravian spanning tree thing, and we asked about what properties would you want this power grid to have. And some of you, one of the properties you mentioned was you want some notion of redundancy, right? If the things break down this way, you want to at least get things that way, right? And that's sort of one of the founding, I shouldn't say founding myths, but it's certainly one of the founding ideas that people like to ascribe to the early internet, that the idea was just like, highways, right? So they just built so Eisenhower had just commissioned the interstate highway system in the 50s, and part of the design of the interstate highway, that the interstate highway was not really designed for you schlubs, right? It was partly designed for the military to get around quickly. So this was driven by Eisenhower's observations when he was in Europe. So he was the commander-in-chief of the forces, the Allied forces in Europe. And what he had seen in the European theater of war is that it's hard for an army to get around when there aren't good enough roads, because armies need to send like tanks and, more importantly, like materiel. And the most important thing for an army is actually what's called supply chain management, right? Because when you go deep into enemy territory, well, the enemy is not going to offer you food and shelter, right? That's sort of kind of what makes up the enemy, right? So in fact, this is of course what happened in 1812 when Napoleon invaded Russia. Russians are like, this is easy. They can't bring food all the way on 1812's highways, by ox cart or something from France. So what do? They're going to forage off the land. So we'll just burn everything and retreat. And like, well, where do we get food from? And well, like, no, you don't get any food. And that's why you have the famous Menard map. There's a very famous illustration of, I'll show you the picture. If you haven't seen the picture, it's useful to know this picture. So it's, this one, okay? So this is one of the most it's like the canonical illustration of it's not that's not a good one. Is that bigger? Yeah, maybe that's bigger. There we go. Okay. So Menard drew this carte figurative, and so basically here, so it's like one of the canonical pieces of visualization. So essentially, what happens is this is the outbound. The tan lines are the outbound army. The black line is the returning army. So it starts off somewhere in France and it ends up in Moscow, and then returns. So the tan line is basically the width of the line is the size of the army. That's it. Like that's your whole story right there, right? But then he does this brilliant thing where he overlays a lot of other things as well. So he talks about the sizes of these different branches and so on. He tells you about the cities. So it's also a geographical map. So that's what's part of brilliant about it is there's a virtual thing, but there's also a physical thing. And what he's telling you about down here is temperatures. And just as a totally nerd geek thing, the temperatures are neither in centigrade nor Fahrenheit. They're in the Réaumur scale. It's one of the few places in the world where you'll see the Réaumur scale. Degree of thermometer de Réaumur. right, which was this weird French scale. It's kind of centigrades done in a slightly weird way. Okay, I've only ever seen the Reaumur scale in the wild once in my whole life, but here it is. Okay, so you can think roughly centigrades here. It's close enough. So you can see that the temperature is changing across time, and you can see where they were at each point in the temperature. And as they're coming back, the temperature is finally going back up, but they basically froze their keisters off, right? And so the land is frozen. There's no food available. So basically, armies don't survive in that situation. So. Anyway, so when Eisenhower was responsible for the Allied war effort, he realized the importance of having good transportation for supply chains for the military. And so he came back to this. He's like, look, if we build that, it'll also be useful for some other things. So let's build like this giant highway network. And let's also make sure that the highway network has redundancy. So there's multiple ways to get there. So this idea of networks of transportation with redundancy were already in the air. Okay? And what was added, so the internet was basically, well, if we can do this for physical goods, maybe we can also do this for virtual goods. So maybe we can also do this for data transmission. Right? But again, it was initially conceived with the military conception, which is the military wanted to have a network by which it can communicate between places, but they gave universities some money to go off and try out this experiment. And there was actually a lot of controversy about how the network should be built. IBM, most of you're not aware of this company called IBM? Okay, yeah. Okay, well, so there used to be this behemoth of computing called IBM. This building is partly as a result of that, right? Watson, who's Watson? The CIT, it's the Watson CIT. Watson was like IBM's Watson, okay? The thing that you've heard of called Watson's named for a human being. That same human being that this building is named for. So IBM was this behemoth of computing, and IBM had a different way of doing networks, which unsurprisingly reflected the IBM ethos. Now IBM gets mocked a lot, most appropriately, because it was all like guys in suits. Okay, they would all wear the same blue suit and like white shirt and a tie, and they're incredibly. It's straight out of like 50s style movies, like Leave It to Beaver kind of stuff. Right? So IBM was this very command and control organization, essentially like a military organization, effectively, except without the guns. Right? So what IBM believed in was networks that were tightly controlled. So you essentially, there were many network designs. I'm not going to get into all of them, but roughly speaking, you would arrange all of the machines on a ring. Okay? So all of the machines are connected on a ring. Now, why a ring? What nice property does a ring have? I mean, setting aside like Gandalf and stuff. Yeah.
Only one cycle.
It has only one cycle. More importantly, to what I've been saying so far. Yeah. It's got two directions, exactly. It's got two directions. Redundancy. Okay? You can send things around in two different ways. Okay? So essentially, IBM and other and there's lots of technical things going on here. But essentially, what would happen is these machines would all be connected to this ring, and if they wanted to send a message, they would come and tell the ring, "I have a message to send," and the ring would say, "No, somebody else is using the ring. Hold on," right? And then after that, well, it would say, "Yes, you may use the ring now." Okay, roughly speaking, I'm grossly exaggerating, but this is I'm not trying to teach a networking class. It's not even what I came to class to talk about today. So, okay, so you would ask for permission, you would send something out on the ring. And then you would control, you would basically, like one version of this is you would get control of the ring, you would send your message, and then you'd be done. And then a few people, Paul Baran and a few others, had this very amazing idea of what they call packet switch networks. So what they said is, look, no. This is a terrible way to use resources, right? Because what happens if one person's sending a really long message, another person can't send a message at all? It's like, well, what else do you expect? They said, well, but now think about that from a fairness point of view, right? Let's say the two of you are trying to communicate, and let's say the two of you are trying to communicate, right? You've got the ring, so you get to control your message and send it, you get the whole message before anybody else is pestered with anything, right? But you don't get to say anything at all. Well, what if we could let you send part of your message and you send part of your message, and then we sort of interleave the ring, right? Interleave the ring usage. Oh, let's make an interleaving ring. They're like, well, what is the quantum of interleaving? How long do you get to communicate before you have to? And then how do we coordinate all of this? Oh, let's make a central coordinator. It's like, this is just getting more and more and more complicated. But if you're used to thinking hierarchically, this all makes sense, right? You have a central coordinator, you go to the central coordinator, you say, can we please get permission? The central coordinator says, after, in 10 seconds, they're talking right now, in 10 seconds you may speak, right? This is like my classroom, right? You can't just yell out things unless I tell you to yell out. You have to raise your hand and I have to call on you and stuff like that, right? So you are used to this, right? And it works very nicely for me at least, right? So we should take the same idea to networking, right? That was how networks used to be built. And IBM was like, this is obviously the way to go. But then these other people had this wacko idea. They said, look, let's not do this. Let's break information up into little packets, okay? And what we'll do is we'll just send the packets out into the network. All of us can send them whenever we want. Okay? Well, so that means, so previously, when I wanted to communicate, when this node wanted to communicate with this node, it would basically make a reservation of the ring, or at least part of the ring, right? So one of the nice things about the ring architecture is this node can still communicate with this node at the same time, okay? So basically, this node would say, I'm about to send a message to this node over here, and this part of the ring would get blocked off, right? Oh, it's like electrical switching, so it's pretty fast. It would get blocked off. So it was obvious where a message had to go, and it would stop over here, right? It was all part of a single flow, is the word. It was all part of a single flow. Well, yeah.
Why can't multiple messages be sent at the same time over the same area?
Well, part of it is, okay, so conceptually so here's the thing about networking and systems in general, okay? Conceptually, every model is perfectly feasible, okay? A lot of it comes down to what is the cost of that model, and the costs are all strange. Sometimes the costs are, well, when I did it this way, I could use just one bit of information, but when I do this other thing, now I have to use n bits of information, and now all of a sudden I have to pay the cost of the n bits. Sometimes there's hardware costs, right? Like maybe when I do it this way, I can just reserve part of the network. Otherwise, I need devices that are going to say, well, which packet goes where, right? So now I have to add extra hardware. Maybe the hardware has a limitation. Maybe in our era, we don't know how to make the hardware fast. A certain kind of hardware we know how to make fast, and certain kind of hardware is slow. And we're stuck with, we want fast hardware, right? We want networks to work fast, and therefore we're going to go with whatever is fast. That's actually something that still very much happens today. Okay? There's a certain kind of network architecture called a TCAM, which I will try to talk about if we get time to get to it. And TCAMs are really fast, and because of that, we use protocols that work well with TCAMs. Okay? So conceptually, everything is possible. It's all a matter of what cost you're willing to pay in terms of monetary cost and delays. Okay? All right, so the packet idea is let's break things down into packets, and everybody can send packets onto the network whenever they want. So every packet, every individual packet now needs to contain information on where it is going. Right? Because we don't have a reservation anymore. It's just that this thing is like throwing out packets, this thing, and maybe this thing now can have communication in two different, it's sending some packets over here and some packets over here. Right? It's starting to talk to all of these different people at the same time. Other people are talking at the same time, and every packet has to identify where it is. It actually says where it's coming from and where it's going to. Okay? So you've actually done something complicated. You've added another component to the network, right? Something has to get this packet and decide what to do with the packet, where to send the packet. And these things are called routers, or routers, however you want to pronounce it, okay? They have to route the packet. So what ends up happening is the router, essentially a router is a giant const statement. That's what it is. It's just a giant conditional. It's a table that basically says if you want to send this packet, you want to send a packet here, you do this. You want to send a packet there, you do that. Now what does do this and do that mean? Well, there might be a router over here saying if you want to access this node, you send you get this packet and you send it out along this edge over here, right? So a box. No, not shopping. I don't want to buy one. Right? It looks like this. They're all very beautiful machines, okay, as you can tell. Okay, well, okay, sort of not like that, but yeah. Yeah, something, yeah, here we go. Well, they're all home routers these days. Okay. Let me see this. Okay, there you go. Like absolutely beautiful, beautiful piece of machinery. Okay? It looks kind of like this. Alright. Alright? So it's got all these things that you see, all those holes there are basically Ethernet wire jacks. So they're Ethernet wires going different places. So it's got Ethernet wire, and maybe this is an Ethernet wire. So this box over here has an Ethernet jack that goes into some like fiber optic cable, and then the fiber optic cable runs for another 1,000 miles and comes out of the ground over here. Right? That's basically how it works. So you have these routers that know how to route things to get to an eventual destination. Okay? What happens if this node wants to send a message to this node? So the router gets a request saying, please send a message to that node. Right? It's not connected to that node. So what it does instead is it sends the message over to here. Okay? What's over here? Well, here is another router, and that router says, aha, you want to send a message to that node, I know how to forward it along. Okay? Yes?
How did that router know to send along?
How did that router know to send it over there? That is a great question. Okay? In fact, it's also not clear that's what it should have done, right? Why? Point. Make your point by pointing. Up, down, left, right.
Right.
Up a little bit. Right a bit. Right there. Right there. Yeah, maybe it should have sent it along this edge instead, right? Maybe it should have sent it along this edge to go here to then be forwarded over there, assuming this node knew how to send things along, etc., right? Well, here's a question. How should it decide what route to take? Something sound familiar? Yeah, the D word, Dijkstra. Okay, so what it's actually doing, what routers are doing all the time behind your back, is they're running a protocol called OSPF, and what OSPF is doing is it's basically solving Dijkstra's algorithm to find the lightest weight paths, right? Where lightest is of course a function of many things, right? It's like typically it's how long it takes to communicate. That's usually the weight, but it might also take other things into account, like what is the congestion on this, or how burdened is this node right now, things of that sort. Okay. The thing is, there is no central controller for the network. If IBM had built it, there would be. It would be sitting in Armonk, New York right now. Okay? But since IBM did not get to decide how the internet works, there is no central controller for the entire network. Instead, all these nodes are constantly talking to each other, passing along information about their neighbors and about their neighbors' neighbors, basically our friends of friends, right? And our friends of friends of friends and so on. They're passing along route information, telling each other, this is how long it seems to be taking for packets to travel along this edge and along that edge. Okay? So these protocols are doing a distributed version of the Dijkstra shortest path algorithm. Distributed means each node is computing part of that graph information, transmitting it to other nodes, which are then combining the information from other nodes to get information on what to do. Okay? Does that make sense? Okay, so there's a distributed Dijkstra shortest path, and the distributed part actually makes life more complicated, but that's actually what's happening. There's a big distributed Dijkstra shortest path running to figure out what all of these, what the distances are, right? So essentially, you can think of this node as having broadcast information saying, I have two nodes that I know how to talk to. These are their IP addresses, okay? So I'll get to what an IP address is in a moment. These are their names, okay? These are the names of these nodes. This node has this name, and this node has this name, and this is how far away they are from me. That information gets propagated here and here. This node takes that information and says, well, I'm connected to this, and I'm connected to this, and these are my weights, and so I'm going to add these weights and pass it along. This now knows, I seem to have two different ways of getting to these nodes, this way and that way, and these are the weights of each one, and then I can figure it out. But I also now know that I have two different ways of getting there, and because I have two different ways of getting there, if so here's the problem. A packet comes from here, and this node says it's bound for there, so I'm going to pass it along this way. Okay? And then what happens? Yeah.
We hope that they pass it.
We hope. We hope. That's the problem, right? Networking is it's all like faith-based forwarding, right? I hope that that packet will actually go to the place that I want to send it to, right? Well, so let's say that this node happened to pick the dotted path instead. Okay? So first of all, the first thing is you don't just send a packet. Every packet that you send also gets an acknowledgement back. Okay? It's got what's called an ACK packet. ACK is short for acknowledgement. It gets an acknowledgement packet back, basically saying, I got your packet. So a lot of the engineering of networking is figuring out what exactly to do. I send a packet. What happens if I don't get that acknowledgement? If I never got acknowledgements by design, then I'd have no idea what's going on in my network, right? So what people did is they sent acknowledgement packets back saying, I received your packet. So what's the problem?
Which node will send the acknowledgement?
Okay, so it's just the node. So the packet came from here. It got forwarded along here. It just makes an acknowledgement. It doesn't know what happened after that.
So only the next node.
That's a conceptual model, right? Yeah.
So wouldn't we want the first neighbor to only send an acknowledgement if it has...
Yeah. So there's lots of issues, right? What happens if you don't receive an acknowledgement is the more foundational question. What if I don't even get an ACK? And more importantly, ultimately, this thing wants to know, not that its packet went over here, but it's like, imagine if you had a shipper, right? Some of you have probably ordered something on Amazon or something like that, right? And you've used FedEx for tracking. Okay, so imagine, this is the right way to think about it, right? So from the shippers, from Amazon's point of view, your packet made it to Louisville. Done. Like, no, that's not good enough. It's got to get from Louisville to Warwick, Rhode Island, then Warwick, Rhode Island to your house. And otherwise, Amazon has to resend the packet, right? So you need to know some sort of end-to-end guarantee. Okay? I'll get to that in a moment. You had a hand up.
I was just going to ask the
Same question.
I was gonna ask. Come back to me.
Okay.
So when you send a packet, do you forget do you lose the packet information?
So it is the responsibility. So there's more stuff going on. All right. Okay. I will end up covering that when yeah.
How do you prevent man-in-the-middle attacks?
I don't know what that is. Hold your thought. Yeah.
How do you know that your acknowledgement was received?
How do you know the acknowledgement succeeds? That's the other problem. Because everything here is a distributed system. Okay? You don't control anything. You don't know anything about what's happening in a remote place. So your send could fail, your acknowledgement could fail. Yeah.
So if I'm like a specific node, why should I use my electricity to send somebody else?
That's a very good question. We should get to that. Hold that. Ask me that question. Ask me both of those questions later. Okay? Okay. Yes.
Can we number the nodes for...
That's exactly what I was going to do next, okay? So what I've done is I haven't actually told you anything about how we even identify a node. I think I'm not going to get to what I want to in class today. That's fine. Okay. I'm at peace with that now. Okay. We have to somehow name a node, right? We've got to name a node. So for example, this machine has a name, right? It's called Tourmalet, right? So if you go on the network and you try to talk to Tourmalet, this is the machine that would respond. Don't try, please. Don't try breaking my machine. Okay? So machine has a name. But how do I tell the world about my name? Well, there's a system called DNS, which stands for Domain Name Service, which is how you look up names. Okay? So if I want to go to, actually, do I have NSLookup installed? I'm not sure. Okay, good. Okay, so basically, CS Brown EDU happens to have a particular address. Okay? And it looks something like that. It's like some 128, 148, 32, 12. Okay? So what happened was a message went to a server, a domain name server, and the domain name server came back and said, this is the address that you're looking for. When a node sends a message, it does not send a message to CS Brown EDU. So somebody, you're sitting at home over winter break and you're trying to find out about your spring classes, so you go to your web browser and you type CS Brown EDU/courses, right? There's not a packet saying, I'm trying to get to CS Brown EDU, I'm trying to get to, there are no strings on the internet, okay? Instead, what happens is that packet, that payload, says, I'm trying to get to 128.148.32.12. Because otherwise, you would be trying to hash that name at every single node on the internet, and it would be a complete disaster. Okay? So the only way you get fast routing is by having numeric indices. And so you get this 128.148 address, and now what each router is asking is, how do I get to 128.148 dot something dot something? Okay? Now, let's look up okay? So, anything stand out here? Something should stand out a little bit. Talk to your neighbors and tell me what stands out.
It's also kind of odd that the canonical name for it, CIS.
Okay, what stands out? What stands out?
128, 148.
128, right? Is that what anyone else have a different answer? Yes?
The redirect?
Yeah, there's a redirect, yeah, whatever. But the interesting thing is the 128, 148, right? What's going on? It would be completely unscalable if everybody had completely unique names on the internet. The way the internet scales is by giving a block of names to a particular party and reserving that block of names for that party. Okay? So this is not different from email addresses. Right? Now, of course, all of you have Gmail addresses, and that's a little different. But imagine your Brown EDU email addresses, right? Supposing you could come to Brown, so you can come to Brown. Actually, I don't know, are you allowed to make up your own names?
Yeah.
Your email addresses? Okay. Some of you think you can, some of you think you can. I'm not going to get into this. I'm not going to guess. Let's say, doesn't matter. Okay, let's actually say you could. Let's imagine you could make up your own email address. Okay? But let's say you were allowed to say, my email address is, that's my email address. That's it, the whole thing. Okay? And anybody in the world sends me email, it's going to go over there. Right? What this would mean, now, besides the megalomania of this attitude, okay, what this would mean is that every email system in the world would need to have an entry for Sriram to know how to send that email message to get it to my machine. Okay? And so now, if Noah decides Noah wants to be Noah, every email system in the world needs to know about Noah. Right? And so on. Every single one of you would have your own email addresses, and like think about the size of that table that has to store all this information, and think about all that updating that needs to happen, right? A new person comes, every entity in the universe needs to be informed this is new person with this email address and it's over here, otherwise it would never get anywhere. Nobody would ever be able to get email, okay? So what did we do? We said we're not going to do that, we're going to do namespaces instead, right? We would do @brown.edu. @brown.edu. Okay? And what this achieves is a very nice separation of concerns. This thing, everyone needs to know how to get to. Okay? But then, this thing is completely internal. So everybody needs to know how to get to brown.edu. But there's far fewer brown.edus than there are individuals in the world. And then once it gets to brown.edu, that sort of last mile problem is delegated to brown.edu. There's a mail server at Brown, and it says, you want to deliver this to Noah? I don't have a user called Noah, or yes, I have a user called Noah, and I'll put it inside their mailbox. Does that make sense? You see how that scalability is gigantically different, right? And the number of these is much smaller than the number of these. Way smaller, right? And in fact, what happens internally is no longer the outside world's business. It doesn't even know whether this is a valid address, right? Maybe you can write Noah plus 23, and the outside world doesn't even need to know. Maybe you allow weird things, maybe you don't. Yeah?
If you want to make a temporary email, so they have a bunch of like weird like at blah blah blah, and they keep them changing. So like, how does that fit into this model?
So those again, so one way to do it is with the plus sign. So technically, if you read the email, the request for comments for that decides email addresses, the plus sign is a valid symbol, and the convention is everything after plus is ignored. So you can make up fresh email addresses by just writing plus something, okay? But the real problem has become, and I used to do this, the problem has become idiots who design websites don't know what the formats of email addresses are. So you type this into email websites and they're like, sorry, that's not a valid email address. So that no longer works. But the way that works is people who do that, they control their own domain, and then they make up new names inside their domain. And the mail gets sent to the domain, and then their mail server inside the domain deals with it. That's how you make up new email addresses on the fly. Okay? Okay, now the same principle, now did this principle make sense? This separation of concerns. There's a high level thing and a low level thing. That's the same thing that's going on over here. 128.148 is brown.edu, and all brown.edu domains are going to be under 128.148. And then there is one machine or set of machines that corresponds to 128.148. The suffixes are all routed internally, just like the prefixes are routed internally in email addresses. Does that make sense? So naming happens this way, but it's actually a hierarchical naming system. And this is the externally visible part of the hierarchy. And the internally visible part, I mean, it's like visible, but nobody really cares. Internally, routing happens, and then the outside world doesn't need to know, doesn't need to store a table with every possible machine. Like, Tourmalet doesn't need to be on anybody else's table. It only needs to be on some very local table that's actually like that, a table for some device up there. Yeah?
Do you need to, or like, do DNS servers give the level of granularity that is necessary? As in, like, because I know some address spaces are.
Yeah. So that's part of what a modern DNS server will do, is to tell you like how much information you need to get the routing done properly. Okay. So what's actually happening is this machine. Let's say this is. So I'll give you your names now. Okay. This is CS Brown EDU, but this is the externally visible name. It doesn't actually exist in the network, so to speak. Right? It's 128.148.32.12. 128.148.32.12. This is brown.edu, which is what? 128 what?
252.
What?
252.
252.
151.
151. Okay? And so this might be the machine that handles all 128.148 star packets. They all come here, and they get routed from here. Okay? So that hierarchy is absolutely vital. And so when you buy a new domain, in some sense, you're reserving a chunk of the address space. Okay? And we've also, the problem is we've run out of address space. So the original Internet Protocol IP had 4 of these. So it had 4 positions with up to 255 values in each position. And that's turned out to be way too small. Okay, just absolutely too small. Also because you're saving off a chunk, right? Like Brown has, it's not, Brown is not like an evil player and saying, I'm just saying like a domain like Brown has captured off 255 times 255 addresses, right? That may not even be enough for Brown. Think about it, what's 255 times 255? 255 is 256. 256 is 2 to the power of 8. So 256 times 256 is 2 to the power of 8 times 2 to the power of 8, which is 2 to the power of 16. What is 2 to the power of 16?
10 to the power of 4.
Yeah, so it's about 65,536. It's not exact. It's not about. It's exactly 65,536. That's not an awful lot of devices, right? Like, I mean, how you all have like 6 or 7 devices each of you, right? So, no, seriously, if you have 7,000 students, and if you take staff and everybody else together, that's about 12,000 people, right? 12,000 people means now we're talking about 5 devices per person, and we've hit our 65,000 limit. And you're thinking, oh, well, I don't have 5 devices, but if you start thinking about like that clock in my office and the thing that's monitoring the temperature, no longer thankfully monitoring the water level of my plant, those are all devices too that are also on the internet, right? So it's a little tricky, okay? Yeah, so naming, numbering, that's how routing works. I'm not going to go into a lot of detail about how the redundancy works, but essentially you get these ACK packets. The acknowledgements have to traverse all the way back, and every packet, so this node might also decide, you know, this edge has been a little flaky. I'm going to send the packet along both nodes. Or it sends the packet along this node. This node does not respond in time, so it says, aha, I'm guessing this thing is down, so I'll send it along here. But it may be that this is actually working, it's just really, really slow, right? So now the same packet shows up twice, and now this destination is going to get the same packet twice. Does that mean it's going to get the message twice? It's going to like append that text 2 times? So what they do is they add a sequence number. Because the other problem is, it might send the first packet this way, the second packet this way, and the third packet this way, and maybe the fourth packet this way. So they might show up in all sorts of orders eventually, right? Ordering is really hard, and there's no total ordering. So for both of those reasons, to avoid duplication and to know how to put things back together in order, every packet also contains a sequence number telling you what order of the message this is, so that you can reassemble it into order and throw out duplicates. Does that make sense? Okay, that's about sort of the redundancy aspect of the network. That's how you need that, otherwise the redundancy would cause a disaster. Okay? Once you do that, you then have to worry about like, you know, load balancing and stuff like that, and so these nodes periodically ping each other, but they don't transmit, this is the critical thing. Brown.edu will not transmit all this internal information to the outside world. From the outside world's point of view, once it's delivered to brown.edu, it's done delivering, and it's not going to care about how things are routed internally. Brown might do the same thing hierarchically inside Brown to make sure that it can get load balancing inside Brown. Okay? But from the outside world point of view, it just gets one address, brown.edu, in this table, rather than this giant set of tables having to do with like your laptop and your cell phone and your this and your that. Okay? Does that make sense? Okay. Now, questions. What were some of the open questions? Yeah.
So like if someone founds Purple University and they want to like connect it to the internet, how would that change? Like,
so what happens is, so this is actually a thing that happens if you go register a domain name. Okay? When you register a domain name, you buy a new domain, okay? And then you go to the domain registrar, you buy the domain, you pay them like an ungodly amount of money for it, and then they are responsible for, and I mean, it's not just the domain, you also have to register some machine that's going to answer for that domain. Then there's a process of notifying DNS servers. So you notify a DNS server, it notifies other DNS servers, it notifies, and that's why if you buy a new domain and set it up, it takes several hours before you actually can access your own domain. Because all the DNS servers have to get notified, and that's like, essentially it's like a call tree. Right? It's like a good old-fashioned call tree, like one DNS server will call all of its buddy DNS server and say, hey, I got some new entries today. And then they'll call and say, hey, I got some new entries today. And it takes some time for it to propagate across the internet. And it can take anywhere from an hour to 6 hours to sometimes as much as a day, depending on where you are. Like if you're in a country that has slow internet access and doesn't contact regularly or something like that, it can take some time for your local DNS server to know that that domain now exists. Yeah?
Who controls the DNS servers? Like if they're private companies, what if they go bankrupt?
Well, so there's redundancy at the level of DNS servers, but there's a much bigger problem. Who controls the DNS servers? What prevents somebody from sending false information to DNS servers? Not a whole lot, it turns out. So partly what has happened over time, so the internet was created ironically for a system that was meant to be for like national security and transmitting secure documents, has almost no security in it. So part of what has happened is people now use trusted DNS servers, and if some new person comes along and says, I'm a DNS server, they're like, no, you're not. You may think you are, but I'm just not listening to you, right? So if a DNS server broadcasts and nobody listens to it, is it a true DNS server? Not really, right? So these rogue DNS servers basically don't get listened to, and a lot of the internet engineering is listening to trusted DNS servers and not listening to untrusted ones, okay? So so I want to get to backbones and man-in-the-middle attack. Yeah.
You told me to come back.
Yeah. What was your question?
So why do people in the middle care about sending?
So these are both. I'm going to answer two questions now. Okay. Why is this person in the middle interested in spending their electricity and their human resources and whatnot sending messages around? Okay, because this picture is a lie. All right. This is not what the internet really looks like. The way the internet really looks is there's a small number, well, they're not small, but there are what are called administrative domains. And there are administrative servers that control these domains. Roughly speaking, you could think of things like, well, okay, how much do I want to lie? Let me lie a little bit, but not too much, okay? So you can imagine that there's Verizon over here. Okay. Now, I know you like to mock Verizon for cell phone service, but without Verizon, the internet shuts down, just so you know. So don't mock them too much. Okay. And there's, AT&T over here, right? And there's, well, not Comcast, but who are the other players? Then there's other big players you haven't heard of, and then there's also entities like Google over here. Okay. What's actually going on is that I think Brown actually works with Verizon. So Brown.edu is a tiny bubble that connects to Verizon. Okay? Whoever we connect to, let's pretend it's Verizon. We connect to Verizon. Okay? And similarly, maybe, I don't know, Princeton connects to Verizon. And maybe, actually, no, Princeton almost certainly connects to AT&T given their location. Because there's a huge AT&T hub down in New Jersey. Okay? And maybe Harvard connects to Verizon or something like that. And then there are these giant pipes of information that connect between these things. Okay? So what's actually happening is it's not. So a lot of this discussion of net neutrality is by people who don't know how the internet actually works. What's actually happening is there are these giant pipes, tubes, running between these enormous entities, and these enormous entities get paid to send packets around. Okay? So part of the argument is, well, why should this node pay? Well, because usually the amount of traffic going on, the amount of traffic coming in is roughly the same, right? So it sort of comes out in the wash. That's a kind of weak argument. But the strong argument is somebody is actually paying hard cash for it. So Brown connects to somebody. Brown pays that somebody. We lease a line. We lease a line with a certain amount of capacity, and we pay for that capacity. We pay not only for the wire that runs to that entity, we also pay that entity to send our packets out and bring our packets back in. Okay? There's lots and lots of very cold hard cash being transmitted. That's why the packets are being sent. It's a very simple answer, actually. Okay? But so what's actually happening is there's a giant, what's called the backbone of the internet. The backbone is these big entities talking to each other over enormous capacity wires. There's a small number of rooms that are actually the physical internet. So part of the reason why people were thinking Amazon might move to Northern Virginia, and they did, but maybe that's for unrelated reasons. Part of the reason Amazon actually has data centers in Virginia is outside Dulles Airport, roughly in that area outside Dulles Airport, is one of the biggest concentrations of the internet. Okay? So we think of the internet as like clouds and stuff, but there's actually physical rooms with racks of routers with enormous pipes coming in, giant cooling systems, and ex-Marines standing on the outside. Okay? That's how the internet actually works. So there are these massive centers that do much of the routing. And then from there, it's hierarchical. Okay? There's, in fact, what was the name of the wire? A few years ago, if the stuff interests you, there's an article you have to read to make the sort of, yeah, it'll come back. What's it called? Mother Earth. Look for Mother Earth motherboard in Wired. It's by a guy named Neil Stephenson who's writing. I don't care for too much, but this is like an absolute classic article. Sorry, yes. It's yeah, I know. I'm not a geek enough for something. So Neil Stephenson wrote this article about how the tubes of the internet are actually laid out. Okay, he calls himself the internet tourist and goes and sees the laying of the internet wire. So we think of the internet as this very virtualized thing, but it's actually huge amounts of physical wire. And a few years ago, Microsoft actually paid to have a huge wire installed from, what was it, like across the Atlantic. There's like all these wires that crisscross the Atlantic, and that's how your data actually gets transmitted, right? There's no actual cloud. There's just lots of physical buildings. So this is how information actually goes. It goes from here, maybe, I don't know, let's just say this is Princeton, this is Brown, and I'm trying to send an email to my friend at Princeton. It's actually going through some route to get to Verizon, and then essentially gets sort of warped over to here, and then gets through some complicated route over here. There is no actual direct connection over here. That would be insane. It would be completely cost ineffectual. And these things, the critical thing is, these things are not all equipotent. They're not equipotent. These things are way more potent than any of these things, and they have to be because a lot of money gets spent on making them good. Yeah?
So if there isn't a direct connection, like what are these scientific research networks like Internet 2 actually doing?
So they're trying to build new overlays on top of these, and some of them are involved physical wires, but some of them are also different protocols. So if you go to the physics department, right, the physics department has a massive problem. The physics department gets ginormous amounts of data from CERN. Okay, it's particle physics data, like ridiculous amounts of data. It is so bad that they can't use Wi-Fi. Wi-Fi is too slow to download the amount of data they need. They have to use physical Ethernet. When they buy a laptop, they can't buy this kind of laptop. They've got to buy laptops with physical Ethernet, because without a physical Ethernet wire, they cannot download the information fast enough. That's how much data they have, right? Part of what's happening is the internet was never designed for the kinds of loads and services we're asking for it for now. For instance, Netflix. So Netflix is now rated to be over 20% of the internet's traffic. The internet was never designed for Netflix. Think about this packet switching that I talked about, right? Oh, you can send packets out of order. Think about what a packet out of order means on Netflix. Yeah, it's not even a frame out of order. It just means like random bits in your frame are just sort of coming in random orders. It would be complete disaster, right? So, I personally make a rare political remark in class. I'm a believer in net neutrality as a principle, but there is no net neutrality. Okay, if there were net neutrality, you wouldn't have Netflix. Netflix has to pay hard money and have special relationships. Netflix actually puts servers right there. In fact, all of these companies have buildings where you can put your server inside their building. Okay, and there are what are called peering relationships. Essentially, these big entities agree to transmit data back and forth, and they go to meetings every year, IETF meetings, where they have agreements, they hand out business cards and shake hands on peering relationships to agree to transmit data at certain favorable rates to each other and work out the business deals. Without that, there is no Netflix, right? You would not get any of the packet service that you get right now if Netflix were just like a regular internet protocol just doing what the internet is supposed to do. Scientific data, it's not designed for bulk downloading like gigabytes of data, terabytes of data. It's not designed for any of these things. So all of these are new things that we're having to build, sometimes by leveraging on top of this by changing protocols, sometimes by laying down new physical wires. That's how the internet actually works. Okay? And if any of this is interesting, go take the networking course. So that's networking in, okay, last quick questions. Oh, the other question you asked was about man in the middle. What does that mean? Well, what prevents somebody from impersonating something, right? Like, I could be this machine over here, and I could just start sending data claiming that I am sending data to brown.edu. Okay, so let me give you the horrifying instance, right? So I want to, don't do this, please. I want to make this person look bad. So I'm going to just start sending them packets with, say, child porn in it, right? And it's going to look like it's all being delivered over here. And so the filters at Brown will be like, whoa, what's this person doing? They're accessing child porn on the internet, right? That's a very real thing that can happen. How do you prevent that from happening? What is it in the internet that prevents that from happening? What is it that prevents the internet from making it look like somebody spoofed a request on my behalf to go and download child porn? I'm going to let you take the networking class and ask that question. Thank you. And I didn't do anything I came to class to do, can you people? All right, next class, no more of this. I'm going to actually talk about what I came to class to do.
Honestly though, networking is quite fast.
I don't think that's what's wrong. I don't think. Yes, my IT